Let's take a look at two more tests from 9.4, the direct and limit comparison tests. We're going to start off with the direct comparison test, and it's basically just like it sounds. So let's say that you have an ace of n, so sigma n equals 1 to infinity of 1 over n squared plus 3. So your ace of n is the terms of the series, so it's actually the sequence. So ace of n is 1 over n squared plus 3. So you can see I've graphed it up here in blue. I guess I should be using a blue pen so I could matchy-matchy. But you can see where the blue falls. Here is definitely a big difference there, that it's lower, below, 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 below. And as n goes to infinity, you can't tell any difference. You can't see the difference between 1 over n squared and 1 over n squared plus 3. Because it's below the graph of 1 over n squared, we say that it's less than. So if a sub n is between 0 and b sub n, which is exactly what we have here, our series 1 over n squared plus 3 is less than the series from n equals 1 to infinity of 1 over n squared, we can say that a sub n converges. So there's our conclusion. It's like a squeeze theorem, if you've heard of that or you remember that if you can put a convergent between 0 and a known convergent, and this is a convergent P-series. So we're using that P-series to prove not a P-series, but something that's behaving just like the P-series. Okay, so that's how to prove it with convergence, and I will do an example and do it a little bit more formally. Basically, I'm giving you the visual. You can see that it's less than term for term because it's below. But how would you tell this without graphing it? If you make the denominator bigger, in the case of adding 3, you make the whole quotient smaller. And if it's smaller, it's going to ride underneath. So for divergent, we have the known divergent series right here, 1 over n. That's a divergent P-series. And so our series, n equals, I better do 2 because the ln of 1 is 0. That would be a typo if I didn't do it. Ln n. Okay? So because ln n is less than n, then 1 over ln n is greater than, term for term, 1 over n. And again, you can see what's going on here. The red is above the blue. So if you have a known divergent, then your series of a sub n is greater than a known divergent. And that's what we're saying here, that if you have 0 and then b sub n, which is your known, that's our 1 over n, and then a sub n is our 1 over ln n. And if it's riding above a known divergent, then it diverges as well. So pretty simple. Here's the deal, though. It's got to be perfect. I can't do this test with 1 over n squared minus 3 because it's not actually less than a known convergent. It's larger than. It does converge, but I can't use this test. So I'm going to say this now, and hopefully I'll remember to say it at the end. When you're doing your homework, there's a section for direct comparison, and there's a section for limit comparison. I want you to use whichever one of those two tests is easier for you. If it makes more sense for you, it's going to be right if it's right for you. So don't follow their directions about which test to use. Do the one that seems to be more natural for you. Okay, so let's take a look at, without looking at a picture of anything, let's say we have sigma n equals 1 to infinity of 1 over the square root of n, and let's go minus 1. Okay? Well, you know from the P-series that the square root of n, where p then is 1/2, is going to be divergent. So all we have to do is say, well, we know that if we subtract 1 from the denominator, we're making the whole quotient bigger. So this is actually larger than the series n equals 1 to infinity of 1 over square root of n. 1 over square root of n is a divergent P-series. And so back up here, if our series, which is 1 over square root of n minus 1, is greater than or equal to even to a known divergent, and this is a known divergent P-series, then you can say that n equals 1 to infinity of 1 over square root of n minus 1 diverges by direct comparison. So to prove convergence with this, you want your denominator to be bigger, and so the whole thing is smaller. And to prove divergence, you want your denominator to be smaller, so your whole quotient is larger. So now we go to the limit comparison test. To be honest with you, I really like this one better. It's a little bit more mathy. I hate to say you don't have to think as much, but it doesn't have to be so perfect. So again, A sub n is our series. When I say our series, it's your homework question, it's your test question, your assignment quiz question. B sub n is a series that you know whether converges or diverges. And if you take a limit of that quotient and you get a finite and positive value, then your series does exactly what the one you compared it to. So let's look at some weird examples. If we had done, so we'll go n equals 1 to infinity. If we mess it up a little bit, how about 3 over 2n squared minus 1? Well, we've made the bottom smaller, which makes the whole thing bigger. So to be honest with you, direct comparison just doesn't work. So now I'm going to kind of go back on that whole thing about your gut. What do you think this is behaving like? Well, I see one power in the problem, and it's n squared. So I think that the 3 in the numerator, the 2 and the minus 1 in the denominator really aren't impacting this series at all. It behaves like the P-series, 1 over n squared. So I'm going to take a limit as n goes to infinity of 3 over 2n squared minus 1 over, here's our b sub n, 1 over n squared. When you flip that and do your Bobo-Bot and HDC, so again, that's kind of what you're looking for here, is to get something where you have equal power and that limit equals 3/2. And I think it's safe to say that 3/2 is finite, certainly not infinite, and it's positive. So because the series n equals 1 to infinity of 1 over n squared is a convergent P-series, then our series converges by the limit comparison test. And that's honestly what most of your homework problems are going to look like. They're going to be some kind of a power. You just have to look at it, strip it down, and see what you think it behaves like. You can have power on top and on bottom. So like we could have n equals 1 to infinity of 3n over 2n squared minus 1. So you've got a n to the first in the numerator and an n squared in the denominator. And so when you subtract and really look at the real power of this problem, it's 1 over n because you're subtracting your exponents. So I'm going to take a limit as n goes to infinity of 3n over 2n squared minus 1, and I'm going to compare it to the divergent 1 over n. I'm going to flip it, and I'm going to get that same 3 halves again, which is still finite and positive. And then I'm going to do like I did before. Since the series 1 over n is a divergent P-series, so you're going to be using P-series a lot. It's not the only one, but it is the most used one, I think. Then your series converges by the limit comparison test. Or did I say convergence? I don't remember. It diverges, because this one diverges. They do the same thing. Diverges by limit comparison test. Sometimes half the battle is just deciding what to compare it to. So if you had something like n equals 1 to infinity of 2 to the n over 3 to the n minus 7, just something random like that. When I look at this, I'm seeing the geometric 2/3 to the n. So if we do a limit as n goes to infinity of 2 to the n over 3 to the n minus 7, and compare that to 2/3 raised to the n. Hopefully we won't have to do any L'Hopital on this. We have 2 to the n times 3 to the n over, did I put a squared there? Sorry, n. And then I'm flipping that, so I have a 2 to the n and a 3 to the n minus 7. So those cancel. And when you take a limit as n goes to infinity, technically that's infinity over infinity. So we would L'Hopital. And it's a nice refresher. The derivative is ln 3 times 3 to the n over ln 3 times 3 to the n. And then the minus 7 goes to 0. And our limit is 1, which is finite and positive. So because 2/3 to the n is a convergent geometric, then your series n equals 1 to infinity of 2 to the n over 3 to the n minus 7 converges by the limit comparison test. So again, you have, I think, 15 homework problems. I want you to write it out, do it like I've done it, be thorough, but they shouldn't take long, and I think you'll be successful with them.